Welcome everyone. I'm Gustavo Bejar. I'm the host for the CONVERSE Spring 2025 webinar series. And before we start, I just want to announce our speaker for our next session. That's going to be Claudia Corradino from the Istituto Nazionale di Geofisica e Volcanologia in Italy. And she's going to present about towards improved volcanic hazard monitoring and nowcasting using artificial intelligence and multispectral satellite imagery. And that presentation is going to be on March 11th. And please mind the time zone. We're shifting here, or in the US, we're shifting to daylight savings time. So it's going to be at 4 p.m. UTC -4. And with that, I want to introduce our speaker for today. This is Simone Aveni from the Sapienza University of Rome and University of Turin. And he's going to talk about the satellite-based thermal infrared monitoring of volcanoes, going from hydrothermal systems to effusive eruptions. So welcome, Simone. In Bocca Lupo.
Hi, Gustavo. Hi, guys. Thanks, everybody, for being here. I'm Simone Aveni. I'm a third-year PhD candidate of the University of Sapienza, University of Rome, and University of Turin. Currently working with the Mirova team. And as Gustavo was saying, today I will guide you through this session about thermal infrared monitoring of volcanoes using satellite-based data. So if you're happy with me sharing the screen, I will go ahead. Right. Can you see the screen, guys?
Yes, that looks good.
Yeah, you're good.
Fantastic. So just a brief summary of today's session. We will mainly split it in 3 parts. So we'll go first through some basic principle of thermal remote sensing. Then we'll move into the hotspot detection and quantification, and especially we'll focus on TIRVOLC algorithm and this new method for quantifying the thermal energy associated with this anomaly, and that is the TIR-based volcano radiative power. And then we'll conclude with some applications and case studies. So let's get started. As you all are aware of, volcanic phenomena are always associated with the heat transfer from the Earth crust into the atmosphere. So this heat radiated can be detected by sensors aboard the spaceborne platforms. And the main objectives of thermal remote sensing for volcano monitoring are to detect signs of arrest at quiescent volcanoes, identify the start and the end of eruptions, follow and track the evolution of these eruptive phenomena, and estimate the effusion rate and the erupted volumes. So here in the schematic representation to the right, you can just see a number of volcanic features that, of course, produce heat. And the 3 major mechanisms of heat transfer at volcanic systems are either by radiation, convection, and conduction. From a satellite perspective, the most straightforward parameter that we can measure is the heat lost by radiation. And this is what we will focus on today. So this heat manifests through a number of in a number of ways, and it manifests with special elements that have a temperature above that of the background, and we call these elements volcanic thermal features. So this is a terminology that we will encounter later on during the presentation. And here you can just see a number of thermal features that are associated with basically release of heat. So let's start to dig a bit more into these volcanic thermal features. So these different types of features from space can be identified, and we can roughly link them from active to non-eruptive conditions. And also based on their maximum temperature, this can be generally divided and split into 3 main groups. And these are the high temperature volcanic thermal features, which usually go above 600 Kelvin. And please bear in mind the 600 Kelvin magic number, because it's a number that we will see quite a lot during the presentation. Then if we just step below that, we get all thermal features comprised between a few tens of degrees above the background up to 600 Kelvin. And then we have some very low temperature volcanic features, which are usually associated with like diffuse heated ground in geothermal areas and this kind of thermal anomalies. And just here to the right, you can see a schematic representation of what these thermal features look like. But most importantly, to the very right hand of the screen, you can see that these features all have different thermal distributions. So let's get some basic principles and fundamental laws of thermal remote sensing. You're probably familiar with the Planck's law, which describes the spectral radiance emitted from an object at a given temperature and a given wavelength. Then we also have the Wien's displacement law that allows us to calculate the peak wavelength given the temperature of an object. And then probably the most famous one, the Stefan Boltzmann law, that allows us eventually to calculate the emittance in terms of watt square meters given a temperature of an object, and indeed represents the integral of the Planck curve. So the Planck curve is here represented in this graph to the right. And you can see a number of curves for different temperatures, starting from the sun surface, 5,800 Kelvin, down to molten lava, and then to ambient temperature. Also here, you can see the visible spectrum represented here, which is somewhere between 0.4 and 0.7, 0.8 microns. So why are these curves fundamental when it comes to thermal remote sensing? Different temperatures, different objects at different temperatures emit radiations a specific wavelength. And we can see that this peak changes and shifts towards longer wavelengths as the temperature decreases. So if we take a molten lava and exposed to the lava flow in a channel, we'll have a temperature approximating 1200, 1300 maybe Kelvins, and we can see that the peak emissions are in the shortwave infrared. So that portion of the spectrum comprised between 1.5 and 2.5 microns. Just soon after, we find the mid-infrared between 3.5 and 4.5 microns, and then eventually we get to the thermal infrared or long-wave infrared between 8 and 14 microns. So we see here that for molten surfaces, the peak emissions is in the shortwave infrared. If we go down, we move to 700 Kelvin, we see the peak emissions shift towards the mid-infrared, whilst we have a drastic drop in the shortwave infrared, and not much really has changed with the thermal infrared. And then when the temperature decreases once again, we get a drastic drop once again in the shortwave infrared, also drop in the mid-infrared, but we start to see the thermal infrared kicking in. And this is because we are approaching the peak wavelength of thermal infrared measurements. So let's put this into a satellite perspective for volcanological purposes and see what that looks like. So here you can see this visible imagery. So this is just a RGB composite of visible bands between 0.4 and 0.7 microns. And this is an eruption of Piton de la Fournaise in October 2015. So here you can probably barely see the emplaced lava flow. I can tell you it's still active, and it's poorly embedded and encompassed within this yellow contour line here. So if you look at this image, you can't really see much except for some bright spots just there near the vent, which are probably the hottest temperatures, where the temperature is approximating 1200 Kelvin, so we still get some radiation visible in the near infrared and very near infrared. But what about if we look at the same image acquired exactly in the same time with some thermal band? So this is what the same image looks like in the shortwave infrared at 1.6 microns. So we can see some bright regions that are indeed associated with a thermal anomaly sourced by those components, those thermal features within our lava flow, that it's approximately at 1200 Kelvin, which means it's what is active right now, or what has been emplaced in the last half an hour or so. What happens though if we start to move towards longer wavelength and we move at 2.2 microns? If we move at 2.2, we start to see more brightest region. What is that? That is because the shortwave infrared has a higher sensitivity to slightly lower temperatures. So we can start to see features that are not just at 1200 Kelvin, or pretty much this is a rough estimate, but perhaps we can see something that is 200 Kelvin lower than that. So what about if we then move to the very end of the thermal infrared spectrum at 11 microns? At 11 microns, we can start to see some regions that were not visible at all in the shortwave infrared, and these are indeed the cooling branches of the lava field that has in place a long time ago, well, days ago. No, I'm not exactly sure when. But the interesting thing is that you can still see this thermal signature, this anomaly, days, months, and you will see later years after the eruption has ended and the lava flow is in the cooling process. So just to summarize, here you can see I've added a synthetic mid-infrared channel, what it would look like, because with the Landsat 8, we do have SWIR band, we have thermal infrared bands, but we do not have, unfortunately, mid-infrared. So just a synthetic representation of what we might see if we had a mere infrared channel. And importantly here is, as we move towards longer wavelength, the area that we are able to detect increases from the SWIR to the TEER. At the same time, the minimum detectable temperature decreases from shortwave infrared to the thermal infrared. So this is great stuff. This is exactly what we would like to see when we do thermal infrared monitoring. But this is not often the case, because in order to have higher resolution or relatively high resolution imageries, we do not have as many data, because that means that the satellite gets an acquisition every week, 10 days, it depends on the satellite. So what we end up with most of the time is something like that. A coarser resolution does not really allow us to discriminate between different components or discriminate between shapes or features, but instead give us just a bright spot, kilometer squared pixel each. And within that bright spot, we do know that we have something hot. We don't know exactly what it looks like, but if we just zoom in at sub-pixel resolution, we'll probably see something like that. So let's take the example we took before, and let's simplify everything, assuming we have three thermal components, one which is very hot in the shortwave infrared, 1000 Kelvin, then we got the mid-infrared and the thermal infrared. And of course, also we do have the background, the ambient temperature, because as we know, anything above absolute zero emits radiation, and these radiations are quantified from infrared sensors. So let's take a look at what we can get from satellite from an image like this one. So for each component, so let's simplify everything. Let's assume that in our pixel, we do not have a background, we do not have anything, we just have one thermal component, 1000 Kelvin, and this is its spectral radiance. So basically, this is the radiance emitted at all wavelengths, in this case comprised between 0 and 15 microns, for that thermal component that occupies a given fractional area within the pixel and has its own temperature. So this is, of course, as we said, not the case. So we start to add more thermal components. So we see that our sub-pixel resolution, we get a mixing of different temperatures, components, each having different occupying fractional areas, having different temperatures. And so if we continue and we also add the background, this is what we end up with. We end up with a pixel integrated radiance, which is basically the weighted sum of all the radiant objects within our pixel that do not occupy completely the pixel, but instead just occupy a portion of it. So the pixel integrated radiance is what is needed for us to detect and quantify a thermal anomaly, because what we're really interested in is not the whole thing, it's not the whole pixel integrated radiance, instead is the excess of radiance. So is just the portion of radiance that exceeds that of the background. And of course, the pixel integrated radiance is different as we move from the shortwave infrared to the mid-infrared and to the thermal infrared. So please bear in mind that this is the most important quantity that we can measure from satellites at specific wavelengths. So if we project this sketch here to a flat plane, we actually see what is our thermal anomaly, which is basically the area that give us the radiative power. So what is the radiative power? So the radiative power, if we were able to see at millimeter scale all the thermal components, knowing exactly their temperature, their area, would be basically the heat flux radiated by all is the weighted sum of all thermal objects that are radiating at that given temperature. To simplify that, just because we will need this later on in our presentation, this part here could be simplified taking the effective radiation temperature, which is indeed the average surface temperature of the anomaly weighted by its area and its radiative power. So with that, we can simplify the radiative power equation to include the effective temperature within it. So great. Now we do have all our background. We know how to calculate radiative power, which is what we're looking for. But how do we do it? As we said, we have a very coarse pixel. We do not know the temperature and the area that each component occupy within the pixel. So we need a solution. And a solution was found about a quarter of a century ago by Wooster and colleagues who developed the MIR method. So the MIR method takes advantage of some features of the mid-infrared channel and allow us by relating the radiative power with the excess of mid-infrared radiance, showing this, obtaining this relationship that indeed enable us, without having to know the temperature, the area occupied by all these components, to obtain a number, and that number is indeed the radiative heat flux produced by that thermal anomaly. So this method has been indeed revolutionary in thermal remote sensing of volcanic activity, because allowed us to, by invoking some complex relationship, to convert this radiative heat flux into volumetric flux, and then in turn into discharge rates. So we're able to know what the fusion rates are almost instantaneously, which we can then use to feed the lava propagation models and all these forecasting models. And of course, it can also give us the total erupted volume at the end of the eruption, which if we do put it in a database, we can then start to think in a more long-term scale perspective. So here you can see that with the mid-infrared or the VRP method, we basically fulfill the first, we covered the first range of volcanic thermal features, which is the high temperature above 600 Kelvin. But of course, as any method, it comes with some limitations. So as soon as the effective temperature drops below the 600 Kelvin, as you can see here, the VRP is not really adequate to measure the heat sourced by lower temperature features. And we have a huge underestimation that exceeds the 50, 60, and 70% depending on the temperature. So we're left here with a problem still to solve, which is how do we quantify the energy sourced by moderate to low temperature volcanic features from very low temperature volcanic features. Here you can see just two maps of the Holocene active crater lakes around the world and the fumarolic and geothermal areas. There's quite a few out there, and these indeed require extensive monitoring, because even if they are questioned at this time, we do not know what's going to happen next, and so we need to keep track of it. And most of them, they are placed in barely accessible locations where satellite information is the only surveillance source. So what happens is we need to find a method that allows us to keep track of these thermal features. So let's try to do the same reasoning that we've done before, but rather than taking a very high temperature thermal anomaly, let's take this kind of real life case study. This is volcano in Italy, Aeolian Island, and we have this fumarolic field. So we have our radiative power equation, and we want to retrieve the heat source by this thermal anomaly. So we want to take what's the maximum temperature. It's below, well, uh, it's dominated by temperatures below 600 Kelvin. So we know that the mirror method is not applicable. So what has been done so far to measure these thermal emissions? To measure these thermal emissions, people were left, researchers were left with with this only alternative. We know that we have this pixel integrated radiance, which is the weighted sum of all components. And we can invoke the inverse of the Planck function to convert this pixel integrated radiance into pixel integrated temperature. So if we do assume that the thermal anomaly, in this case, occupies the whole pixel and is held at constant temperature, we end up with a pixel integrated temperature that equals that of the thermal anomaly. So we can rewrite our radiative power equation to put the pixel temperature and obtain the radiative heat flux under the measure assumption that temperature is homogeneous at the pixel scale and the thermal component fills the pixel completely. So of course that leads to a question. So this is what has been done for the past 20 years, but is this assumption realistic? So what I was doing, I took this 3x3 box. This is the Beer's thermal infrared imagery, 375 meters per pixel. And I was just checking what a volcano-fumarolic field would look like if we put it there. And that is basically the pixel, sorry, the thermal anomaly is not a homogeneous temperature, and the thermal anomaly is not filling the pixel completely. And even if we lower the resolution, we take Aster at 90-meter resolution, so it's quite higher resolution compared to the Beers, still we get the same thing. We do have a number of thermal components with different temperatures, but they still are different at subpixel scale. So the next question is, what happens if we keep assuming the temperature is homogeneous and all we said? So by doing some modeling, this is what happens. What happens if we keep saying that the temperature is homogeneous at a pixel scale, we end up underestimating the radiative power emissions by more than 90% if we only get a small portion of the pixel contaminated by something relatively hot. And if we're staying beyond the 600 Kelvin threshold, we're still underestimating by more than 50%. So a solution was here needed. And here we move to the VRP tier, this novel approach that is currently under revision. And this new method to estimate the radiative power from systems dominated by temperatures below 600 Kelvin. So if we take and revise the Huster approach and we take the excess of spectral radiance, but in the thermal infrared rather than the mid-infrared, and we do plot the curves of the true radiative power emitted for unit surface area, we see that beyond the 600 Kelvin threshold, the two curves sharply diverge. But if we're staying beyond that 600 Kelvin threshold, we can see that the two curves closely match. So if we compute the ratio between these two curves, which is the thick line in the right side subplot, we can see the ratio lies within an interval of plus minus 35%. So we were like, well, cool. What about if we apply this to a real life case, like real life scenario? So we synthesized for each wavelength comprised between 10 and 12 microns, 10 million simulations, which is each of these gray dots just for 11.45 microns, the Beer's infrared wavelength, central wavelength. And we realized the relationship holds. So even if we have different temperature distributions, as long as the effective temperature is below that 600 Kelvin threshold, we still can quantify with a 35%, with a plus minus 35% uncertainty, the true radiative power emitted by these volcanic thermal features. And just to validate that with estimated the true radiative power for each of these thermal components using the radiative power equation. We compared it against the tier-based volcano radiative power, and it's just confirming that our uncertainty lies within a plus minus 35% interval. So where is this system best applicable? To a number of systems as the one we mentioned before. So all crater lakes, which are mainly dominated by temperatures below boiling point, fumarolic fields, or hybrid system, which encompass both crater lakes, fumarolic fields, heated ground, and so on. So with that said, that was a brief summary of the volcanic radiative power method. So now we have something that allows us to estimate the thermal emissions from these features. But now the challenge is how do we detect thermal anomalies from space if it's something that is very, very subtle in terms of thermal anomaly. So there are a number of current volcanic hotspot detection systems, and this can be generally subdivided into main families. So those targeting magmatic temperatures above the 600 Kelvin and those below that 600 Kelvin threshold. So when it comes to the hot temperature ones, of course, for the reasons that we saw previously, these are based on shortwave infrared and mid-infrared channels. And you might be familiar with some of these algorithms. So you got Mirror, Modvolk, FIRMS, HotSat, and many more. When then it comes to below 600 Kelvin, these are thermal infrared based, and we have less algorithms that target this thermal feature. So why is that? It's definitely for a number of reasons, but amongst them, probably the two major ones are because mid-infrared has been honestly so useful in the past quarter of a century that, of course, that was the main focus of thermal remote sensing discipline. And second, because detecting subtle thermal anomalies with the resolution of sensors that we currently have is a bit of a nightmare, because we can get a pixel which looks anomalous at the summit of a crater. And then if we move just a few kilometers downslope, we see that the seawater is actually hotter, warmer than the thermal anomaly itself. So statistical approaches to discriminate what is anomalous and what is not is indeed very challenging. Well, no matter, we found some solutions, but what is important to say is that both algorithms, regardless of the targets they want to detect, are based on the trade-off between the spatial and the temporal resolution. So shortwave, infrared, and mid-infrared sensors usually provide data with high spatial resolution and low temporal resolution, such as like Sentinel, Landsat platforms, or the other way around. We have a poor spatial resolution with a relatively high temporal resolution, such as MODIS and polar orbiting satellites. When it comes to thermal infrared, because we want to detect subtle thermal anomalies, then we have a high spatial resolution, but with a low temporal one. So what TierVolk aims to bring in is to provide the highest trade-off currently available with the open source platforms to provide a relatively high spatial resolution with a high or relatively high temporal resolution. So just to provide an overview of the algorithm works on nighttime imageries from the VIIRS instrument at 11.5 microns, and this is based on the assumption that a linear relationship exists between an observed scene and its long-term monthly average. So as we have more than 10 years worth of data, if we just stack all these images together for any given month, we can obtain a reference matrix. So if we take, let's say this is January, so if we take any observed image acquired in January and we compare the two, we can just quickly obtain an image of the residuals. So if we apply some fixed threshold, we can detect the brightest or hottest pixels. But as you can see easily here, although we detected the 3 hottest pixels, we still have this halo around it that was not detected or detectable with fixed threshold without having a huge number of false alerts. But we want to know the full area, the radiative power associated with the whole anomalous area. So to overcome these limitations, we vectorize both the reference and the observed scene, and based on the assumption of this linear relationship, what we expect is to find these data points or these pixels lying around the 1:1 ratio. So anything falling below this is something technically called, which is in general clouds, as the blue shape and patches that you can see there to the residual image. Whilst if we see as something that is an outlier in the upper part of our scatter plot, is indeed thermally anomalous. And this is what we can, this is how we can detect our subtle thermal anomalies. So here you see the orange stars, which are associated with the 3 hottest pixels. And then with this clustering approach based on the Euclidean distance, we can detect all the full region anomalous. So just to provide an overview of the algorithm as based on 2000 scenes, we have a false positive rate below 2% and a false negative rate between 5 and 15%. And at present, we're monitoring 111 volcanoes with this system, but new targets are regularly added based on either volcanic activity or scientific interest. And still, at the moment, we update the system every 24 hours, but the near real time, it's hopefully coming soon. So great, now we have a system that allows us to detect thermal anomalies from space. We have a method to quantify the energy sourced by these subtle thermal anomalies. Let's have a look at what we can obtain and just have a brief idea of what we can obtain from this information. So first challenge is to validate the method. Unfortunately, as I mentioned, crater lakes and geothermal regions are often placed in barely accessible locations, and having continuous ground truth data is almost impossible. Fortunately, though, the GeoNet has a sensor installed Mount Rapeo, which measures in continuous the lake surface, the lake temperature. So these data are freely accessible. Downloaded them. We do know the area of the lake, which has been relatively stable in the past 12 years. So with this information, if we take all of this and we put it into the radiative power equation, we can then take the true radiative power sourced by Mount Rapeo, and you can start to see these heating and cooling cycles that are well recognized at Mount Rapeo. So what happens if we do take the same measure, but exclusively from satellite information with the VRP tier and tier Volc thermal anomalies? This is what we get. So we get basically a remarkable agreement with all data around the 1:1 ratio and with a margin of uncertainty that is well below the method uncertainty threshold. So we now have this measure of the radiative power. So what can we do with it? We can start to see a long-term pattern. So we can see what the steady state or the baseline thermal emissions for a given system are. So if we do the average, the annually average tier emission, we see the Mount Rapeo produces 27 megavolt as a heat flux. So if we take this to be the baseline, the steady state of the system, we can then compare the volcanic radiative energy, namely the in the time integrated energy sourced by the system, and we can start to see how this deviates from the long-term baseline. And here with Rapeo, you can see that at the moment, starting with probably 2023, 2024, we have this deficit in terms of heat emission. And if we want to put that statistically, at present, it reached approximately 3.5 standard deviation beyond the baseline, the steady state. So what the system is doing, and we might start to think about what's the processes related to this signal and patterns that we get. So this is just an example, but we can take a lot of other case studies, and here just taking a subset of what we were able to, locations where we were able to take some ground truth measures from literature. So you can see El Chichon, Tal, Volcano, you can see the Purasé, which we have no ground truth data, but given the thermal arrest, it's nice to see how TIRVOL can measure a volcano entering an arrest phase all of a sudden. Once again, pause, White Island, you all know the story. So this is just these are just a number of examples of what we can get from combination of TIRVOL and VRP-TIR. But let's take a very hot case study, something that is happening right now, and that is Fentale volcano. You probably heard of Fentale in Ethiopia. Just to give a brief summary of the situation, in October there was this huge dike intrusion between Fentale and Dothan volcanoes in the East African Rift in Ethiopia. And then somewhere around the 14th of January, a white blob, this is the way I like to call it, a white blob appeared in the crater. With the first image, we had no clue what that was. We initially thought it probably was a crater lake, although it was a bit unusual. And then we started to get more images, some high resolution imagery. So we started to realize that that was more like gas emissions. The weird thing it was very stable and confined. It stayed there for days. Then on the 19th of January, the Tropomi measured a crazy amount of methane emission in an unusual place. So this tasked a high resolution GHJ-SAT to get some higher resolution information about the Fentale situation. Well, surprise, 1.4 kiloton day of methane emission, which I'm not an expert of it, but people are saying it's a lot. So something is going on at that system. And just this kind of emissions continued. And a few days ago, we had this magnitude 6 earthquake just a few kilometers east from the caldera that originated that focal mechanism, which is indeed very representative of a caldera collapse. And there you go. This is a PlanetScope that was acquired a few days ago, showing indeed the collapse of the caldera, of the Fentale caldera, by quite a few meters. And you can still see the white blobs there. So the question is, what about the thermal signature? So far we just provided an introduction using a lot of satellite data, but what about the thermal? Well, this is just a timeline of what we initially saw. We were looking at visible imageries with Sentinel-3, and on the 15th of January morning, we found this kind of bright spot appearing there that looked like a cloud, so we were not sure what it was. But the night before, on the 14th of January, with TIRVOL, we measured a thermal anomaly inside the Fentale crater. And we were like, well, what is this? We had no clue. And we were just waiting to make sure that was a volcanogenic thermal anomaly, was not related to wildfire anthropogenic activity. But that thermal anomaly continued. So a few days after, we started issuing some informative panels for competent bodies and stakeholders just to be informed about the situation. And we kept giving them an information. We started to get some thermal infrared, higher resolution imagery, start drawing some profiles across the craters, and just start to see what was going on and how the anomaly was evolving. But all of this was possible because we started to detect these thermal anomalies here. You can see them to the very right hand of this plot. So we got nothing for 10 years, just nothing. And then all of a sudden, we started to get this thermal anomaly. Now, to put that in a better context, imagine that we had a peak of 200 megawatts. Volcano, the baseline emissions is approximately 2 megawatts, 2 orders of magnitude lower. During the peak and rest, we were approximately at 20 megawatts, which is an order of magnitude lower. So wherever is going on at Fentale is probably heated ground. We do not know yet what it is. And of course, we need more data to ascertain what is the source of this heating within the Fentale. But of course, it's something that we want to keep an eye on. And of course, in this case, in a situation where we have just a tiny monitoring network, ground-based instruments are basically not existent, this is the only source that we can retrieve thermal information. And likewise, just taking another example in the Ethiopian region, this is the LOL, where one of the probably harshest places in the world where you want to get to. But we still can get a thermal signal. And for instance, here we can see that something happened in 2017. So here we saw some thermal anomalies, some warnings, let's say, some quantifications. And this was just for low to moderate temperature thermal anomalies. But how TIRVOL can be useful also during eruptive crisis? So let's move to La Palma. La Palma 2021, 85 days of eruption, 12 kilometers square of lava field, about 175 to 100 million cubic meters of erupted volume. In this sequence here, you can see the ground truth advancement of the lava flow, the colored shaped files to the top right corner. And to the bottom, with the colored dots, you can see the distances from the ground observations. And with the red ones, you can see the TIRVOL measured distance during the eruption. And that enabled us to provide an estimate of the flow from velocity, which just a few hours after the eruption started told us, well, the flow is traveling 200 meters per hour. So, of course, if you're able to provide that information to civil protection, to competent authorities, you can tell them, well, just do your math. It's traveling 200 meters per hour in that direction. So you probably want to evacuate or, take some actions because this is what the current situation is. But more than that, we can also start to be more quantitative as soon as the eruption ends. So when the eruption ends with TIRVOL, given its high sensitivity, we can measure the cooling curve of the emplaced lava flow for years. And now, just briefly, this is something we're currently working on. If we take a theoretical cooling curve, which is obtained by solving the Stefan cooling problem, we can see that this should be the theoretical cooling curve of a body, an initial temperature that has to reach the ambient temperature. So this gives us an information. We can convert that in watt per square meters. So if we have watt per square meters and we multiply this curve by the area of the cooling lava flow, then we should obtain a curve that stays just envelopes the measured cooling curve from TIRVOL. And this is exactly what we've done. So we know that the temperature, as soon as the eruption stops, drops below 600 Kelvin. We can measure that. We can increase the area. We can multiply by a factor being the area of the curve. And we can see that once we reach the 12 squared kilometers, the curve indeed matches with the observed one. So why is this important? It's important because it can tell us a lot about the energy lost through cooling. It can be important for post-emplacement and cooling dynamics. And also on something that we're currently working on, we can perhaps estimate the erupted volumes starting from these cooling curves. So let's take some other very brief examples. These are just some time lapses of what some major eruptions that occurred in the past 10 years look like when looking at with TIRVOL. So this is Erta Ale. If you look at the bottom here, the colored image, you can see the advancement of the lava flow. You can see the tunneling start forming. You can see the pulses in the lava flow advancement velocity when a breakout happens, or you can see there is not more movement when the effusion stops. And we can do the same, for instance, for Mauna Loa. Here, I do apologize. Initial velocity was 90 kilometers per day. We were able to get that image just an hour and 45 minutes after the start of the eruption. But because I made a mistake, I omitted that image. So the calculation is not right in terms of peak velocity. So we should have an initial velocity of 90 kilometers per day. And similarly, here we get the fog eruption. So we can see this nice initial velocity picking up, the maximum distance reaching indeed the maximum extension. And in this case, the VRP tier is not representative of the true thermal emission sourced by this eruption, but it's more to give us an idea, an appreciation of what's the magnitude and the energy of the event. And just this one that I made a few hours ago, about the ongoing Etna eruption that started on February 8th and is still ongoing at the time of speaking. You can see here how we get the advancement of the lava flow with its maximum distance, the velocity, and an idea of where the lava flow is located and its maximum distance from the summit. So this is just an example of what can be done with this time series, with the VRP tier, with TierWork. But now let's try to put this into a more global perspective. And let's start to think what we can do if we have these information, at least the information where we can correctly quantify heat sources from hydrothermal systems at a global scale. We can end up with some information like this. This is just a subset of the volcanoes that are currently monitored. And for each of them, we can see what is the average thermal emissions, and we can see how much they produce, and we can start to put them into a global perspectives in terms of joules per year. So we can see what is the energy associated to each of these systems, which system produces more than others, what is the sum of all of these systems, what is the role they play in the global thermal budget. So we can start to investigate much more than just looking at trends and just looking at thermal anomalies, but we can indeed make some global scale quantification. And this is just some preliminary evidence. Of course, a lot of work needs to be done, but it's something that we're currently working on, and of course, together with the implementation of the system in near real time, the integration of upcoming higher resolution sensors, and finally the completion of global inventories of thermal emissions from low to moderate temperature systems. And as a last note, I would like to thank all the guys of the Mirova team, the everyday work and contribute, we work all together to get this information out there in the fastest possible way. And just here, this is a panel synthesizing all the institution at a global scale using thermal infrared imageries in their daily monitoring routine. So you can see that's pretty much everywhere. So thermal remote sensing is indeed a valuable and unreplaceable tool for volcano monitoring. And with the new sensors, with the upcoming sensors, with the higher resolutions, we will be able to obtain a lot more. And I'm very much looking forward to be able to see what the future of thermal remote sensing will be. So thank you very much indeed for your attention, and I very much welcome any questions.
Thank you for that great talk, Simone. If you have any questions, feel free to put them in the chat or raise your hand and we can call on you. As we wait for questions to come in, I've got a quick one for you. With kind of the age-old question of vegetation and kind of systems that aren't as visible to satellites, how much? Yeah, go for it.
Sorry, can you say that again?
Yeah, with vegetation kind of impairing satellites' ability to view volcanoes and their thermal signatures, do you see a next round of satellites that will be strong enough to kind of get through thicker vegetation in areas to get a better understanding of volcanism in some tropical areas?
Well, when it comes to vegetation, this is not really my field, so I won't be able to tell you much about it. But what I can tell you is the vegetation, as any surface, any material, has, of course, an impact on the thermal information we get. Because as we were saying, that vegetation will be included in our pixel integrated radiance. So of course that plays a role. I think with the higher resolution upcoming satellites, we'll be able to better discern between vegetated areas and unvegetated areas, and perhaps we could start to put that into scale and see what a vegetated area would like, what the effect and the impact of a vegetated area included in a pixel where we have a thermal anomaly. But at present, I must admit, I didn't investigate that that much, but it could be something that we can look at together.
Thank you for that. Again, if you have any questions, feel free to put them in the chat or raise your hand. Otherwise, I'll keep lobbing questions out there.
Well, hopefully it's because it was clear enough.
Absolutely. We have a question from Nicholas. He says, excellent talk. Will this data be hosted anywhere where it can be viewed in real time? I work with folks in IGN, and I'd love to, and I imagine they'd love to see this data.
Hi there. Thanks a lot for your question. Yeah, well, we are currently working on making this whole system operational. So we're planning to put that in near real time as soon as we can. At present, these data are not available online. But of course, if you think that there might be some data that you're particularly interested at or some targets that you want to look at, just please feel free to drop me an email and I'll be more than happy to share the data that you might think useful for your purposes.
We have another question from Carlos. He asks, Simone, great talk. Information about Purace, is that how you pronounce that volcano?
Sorry, which one?
Purace.
Oh, Purace.
Thank you.
All right.
Information about Purace volcano and the time series you showed. What sensors are those data from?
So you're talking, sorry, did you mention deformation?
It does not ask.
Hi, do you hear me?
Yes, I can.
Okay, thanks, Simone. Great talking, great research work. A question about the information from Purace volcano. What sensor, what satellite sensor do you use in this time series?
Right. All this time
VIRS?
series that you saw is the VIRS, 375 meters resolution thermal infrared band, 11.45 microns. So all the time series that you saw in this presentation were from the same satellite.
Okay, VIRS sensor. The board VIRS, the Suomi MPP and the
you got
NOAA 20 maybe.
That's exactly what it is. Three platforms that have the VIRS instrument amongst their payload, and just let me quickly get that for you. That should be there. Yeah. So those three. So this is
the three
sensor.
ones. Okay, the three. Okay.
Yeah, and
Great.
this is all the data are coming from these platforms.
Great, thank you. For sure,
welcome.
we are interested.
Yeah, please feel free
I work
to
in
drop me.
the Purace Volcano Observatory, so it would be great to talk with you in more detail. Thank you so much.
Absolutely, more than welcome. Really appreciate it. Please just drop me an email anytime and we can discuss that further.
Great, thank you.
Thank you.
We have a question from Andrew. He says, great presentation. I'm interested in the East African Rift Valley system. Is there a correlation between the dormant volcanoes in Kenya, in the Kenyan Rift Valley, and the Ethiopian volcanoes?
This is, I guess, a $1 million question. From the top of my knowledge, I must admit, I have no idea. I genuinely do not know. So it's not even point to giving a guess on this matter. So I'm really sorry, but I don't know what to say about it.
I have another question for you.
Yep.
With like long-term eruptions like we see at Piton de Frenas and Mauna Loa, do you see differences in the thermal signature if you're able to subtract the background away to look at where the lava fields are becoming more active over time?
Well, indeed we can. With Mauna Loa, it's actually a very interesting place to monitor, at least from a thermal perspective. Because just let me get that for you. Yeah, Mauna Loa, if you see just south of the lava flow, you see that bright spot just there. Can you see the cursor of my mouse?
Yeah, we got you.
Good. So if you see that, this is it's not part of the lava flow. This is this tiny bright spot here, which is the sulfur cone. I guess it's a fracture of the 50s or 60s. Can't remember now the date of the eruption. That is constantly monitored by the USGS guys. So to be fair, I've noticed that not too long ago, and I will start looking at the background level of this thermal feature. And it's interesting to see that you can distinguish this thermal background, and I'm currently checking whether some more information can be extracted from that. When it comes to the effusive activity, the great thing about thermal infrared is that you can start to see things that look pretty much all the same if you just look with your naked eye. So if, for instance, we would have a breakout just somewhere there, you'll start to see this bright spot appearing. And so you can definitely see, and another great case was the Ertaale, which is a very complicated and poorly known eruption. If you see here, you start to see all these, like here, can you see here a gap? There is just a gap, and then it gets filled eventually. But you can see all the lava tube systems that is developing, and even the small branches, they are extending and appearing eventually. So yeah, with thermal infrared, even at this resolution, which is not the greatest, but is still sufficient to get daily information, you can start to distinguish a lot of features in the lava field or the advancing lava flows.
That's really cool. Thank you.
Welcome.
All right, we've got another question from Alex. He says, "Thanks for sharing such fascinating work, and I look forward to seeing more access as it grows. I was wondering if the areas of high volcanic activity that were not associated with collaborative organizations, for example, Japan, are not being covered yet due to the early stages of this project, or if the current satellite system doesn't cover that area and we need more satellites set up to monitor these areas."
Thank you very much for your question. This is a great question. I guess you're referring just at the last slide, perhaps, where there was not much on the region. No, satellite data cover the entire globe. So we do have information from the poles to the equator, all latitudes and longitudes. We do have some Japanese volcanoes that we're currently monitoring. I'm not sure if there were collaborations with Japanese institutions, but for sure we are more than happy to share information with Japanese institutions or with people and researchers that do work on Japanese volcanoes. So we do have Japanese targets in our database. So I think it's just it happened that it is not there in this presentation or in this case.
Looks like we have a question from Gustavo. Gustavo, go for it.
Hi, how are you? Can you hear me?
Yes, I can.
Oh, great. Thanks. Well, first of all, thanks, Simone, for the talk. I think it was excellent. It's very breakthrough the research you do. I have a question about monitoring volcanoes in tropical areas where cloud cover can be like a big inconvenience. How do you handle that? How can that like affect the monitoring time series? And yeah, basically that.
Right. You want a 100% honest question? Honest reply?
Yeah.
We usually cry. This is all we do. We sit in a corner, we switch the lights off, and we cry. There is nothing that we can do to deal with clouds. And in the algorithm, in the work where I presented the algorithm, I was doing an assessment of the damage caused by clouds. In tropical regions, during monsoons period, we do get up to 92% cloud coverage. So what that means is basically we have no information whatsoever. And there is nothing that we can really do. Using mid-infrared channels, if there is a very strong thermal activity and clouds are not very thick, we might be able to penetrate clouds and still get a thermal signature, despite that is highly attenuated. With thermal infrared channels, one of the back rows is as soon as we have tiny layers of cirrus, we cannot see through it. So unfortunately, cloud coverage is the worst nightmare when it comes to thermal satellite observations, but there is very little that can be done because that information is basically lost forever.
Right, thank you. That's the answer I was expecting to hear. But anyways, thank you again.
Welcome.
All right, well, looks like we're running up on our end of our webinar session here. Please join me in thanking Simone again for such a fantastic talk. And we hope to see everyone in 2 weeks for our next webinar series. If you would like to sign up for that, you can sign up in the same way you did for this one on the Converse website. And all of these talks are recorded and available online. They will be in the next couple of days for this talk. So if you want to watch them again, please visit our website for that as well. And thank you for attending today. Have a great rest of your day, everyone.
Right. Thank you very much indeed for this opportunity. Thank you very much indeed for joining me. I really appreciate it. It was a great chance and great opportunity to share a bit of my work with you all. And as I mentioned, if you want to know more, if you want to have some additional details, or if you want to just have a look at some more data, or you want to suggest some more targets to be added, please do get in touch. Don't be afraid. I'll be more than happy to get back to you as soon as possible. So once again, thank you very much indeed, guys, and have a great day. Good luck, you all.